David Lange, can you hear me?
Hi, David. I do.
Yeah. So I've put together all the PDF I could find up to 5 minutes ago, and I've put them in one file which is called all together. So I will. There's a few still missing, and I will show this. So I will share this file one speaker after the other.
Okay. Who are you missing? I can just check if I have something in my inbox.
Alors, Brookman, Scambrax.
Okay.
Scambrax. Calderon. Hughes, Hewes.
Sounds like a much lower ratio than past meetings. Okay.
Itai, or I think it's Itai. Yes, Rani Itai. And that's it. So we have 4 missing actually.
Let's see. So I missed one. So it's Sebastian Stenkanks, Will Calderon,
Hughes, Hewes.
Jeremy. Okay, so apparently I missed 2. And who was the last one?
Ran Itai. Itai.
Okay. Let me look in if I have anything from those people or not. Sometimes emails go past and I don't see them. No. I know a few of those are on the west coast of the US, and so we may be uploading when they wake up, sort of thing. Nope.
At least I have the first bunch. First bunch I have.
Did I not manage to list Will Calderon on the speaker list?
So I took all speakers from the Wednesday session.
Yes, that's what you should do.
Plus Daniel Murnane,
yeah,
I've put first.
So, okay, so I think I did not put, so I, by hand, made a new contribution with all the speakers, and I think I left Will off, which might mean I also left him off of an email. So he may. Well, that's unfortunate. Okay, let me add him now in case he figured he should have gotten an email. Will, I don't see Will Calderon on the list of names that I put on the Indigo contribution for today, because I did it by hand.
Yeah,
okay, I've added him, but if he doesn't come, it's probably my fault.
Okay.
And I have all the others though. Faster. Yeah, okay. I have the other three. No, I don't have anything from them. So hopefully they'll upload things late. Let's see.
Hello on Zoom. There is a David connected. Is it the David Rohr?
Hi, I'm connected.
Okay, good. Okay, so for the first batch of 4 speakers, Daniel Mornay, don't see him. David Rohr is online. Lejan Golubovich is online. And Lucas is not connected yet. We just have Ran Itay. So I will include it. Okay, hello everyone. I see that we have a number of people connected now on Zoom. So everyone, almost all speakers have submitted one slide for their work. Just put all of them together. There is a file on Indico which is called altogether something, which you can use for your convenience. So we should be started, and then I will show the slide, and then you will have 1-2 minutes to explain your slide, and then we open the floor for questions. I just lost my Zoom window, so but hold on, and we should be starting very soon. C'est partagé. Do you see my slide? David?
Yep.
Hi, David.
Yes.
Yeah.
Okay, thank you. Thank you. Thank you. Okay, so is David Murnane online? Yes, I can see you. So there was a Zoom crash yesterday when you were just starting. So we'll restart with you. Daniel Murnane, sorry, not David. Daniel Murnane. Can you hear me? Okay, so we give a chance for David Langer. Anyone can unmute himself. I don't need to unmute people, right?
No, everybody can
Okay. Okay.
unmute themselves.
Okay. So then we move to the next one, and we give the chance to Daniel later. Next is David Rohr. David Rohr, you're online.
Yes.
And so I'm sharing your slide.
Thank you. So my talk was about Alice online and offline processing for LHC run 3. So basically what Alice will be doing is let data taking at 50 kilohertz interaction rate. Alice will do only minimum bias data taking, no trigger, continuous readout, everything processed in software. We have a major upgrade of our detectors. In particular, the TPC is changed to a gem readout, and we have 7 layers of silicon pixel tracker for the upgrade. This comes with several challenges, in particular for the TPC. The most important ones are the calibration for the space charge distortions, the data compression of storing 50 times more events than before, and the tracking in continuous readout without a priori knowledge of the Z coordinate of the hits. For the processing, we foresee a scheme very similar to what LHCb is doing, so a two-stage processing with a disk buffer in between, synchronous processing while there's data coming in for calibration and compression, and then the full asynchronous reconstruction when there is no beam. And we will use GPUs to speed up the processing. We have two possible architectures that fulfill our needs, which is AMD Vega 20 and NVIDIA Turing. And our estimate is that we'll need around 2,000 GPUs for the processing of the synchronous part. And then, of course, at the asynchronous, we want to use the GPUs as good as possible.
Thank you. So anyone has any questions? So please raise your hand. Or if you're confused on how to raise your hand, just go ahead. Any questions to David? One simple one to start with. Do you have any trigger actually in Alice?
Well, we had trigger in run 1, run 2, but the idea for run 3, at least for LED, which is the primary purpose of Alice, is to run triggerless to store the full minimum bias readout. So we can basically look for rare signals with high background in the minimum bias data. For PP, it's not fully decided, so there might be a trigger scenario for PP with high interaction rate, but this is not decided yet. This is just an addition maybe that could come. And
so you're keeping everything. So can you store all the information of the event, or do you have to do some reduction of the event and losing some online reconstruction and dropping
yeah, so we have quite elaborate compression algorithms, which is not completely lossless. So basically what we do is we don't store the TPC raw data, but we clusterize the data on the fly, and then we store the clusters. So of course because we cannot store the raw data. And then also we do tracking, and we identify tracks that are not used for physics, like stuff below 50 MeV and tracks looping in the TPC. And then we remove the clusters of these tracks. So that part is also lost.
I see.
Besides that, we store the full information.
Okay, and the guesstimate of the amount of data per year?
So the disk buffer, which is dimensioned for 1 year of LED data taking, but that is essentially, 3 to 4 weeks, is the 60 petabytes. And then on top of that comes the PP.
Okay, 60, you said 60.
60, yes.
Okay. Any other questions? I see Joe Osborne. Joe?
Yeah, so David, I just have a question. Your bullet point here says tracking in TPC with continuous readout is one of the problems. And I assume this is partly due to the space charge distortions, or the space charge distortions make tracking in the TPC difficult. So can you just comment on how Elise is addressing that problem?
Well, you have two problems. They are kind of related. So we have these space charge distortions. They are a problem per se to track them. What we have to do there is this calibration procedure, which was explained in the talk. So we have a track-based compression and then compression that integrates the currents arriving at the end plate. And from that, we can basically compute a correction map for the cluster. Now, the problem is, in order to apply this correction to the hit, you need to know the XYZ coordinate of the hit. But in continuous readout, where you have events overlapping in the TPC in time, which means in the Z coordinate, we don't have the Z coordinate of the hits a priori. So that is kind of a chicken and egg problem. So we have kind of an iterative tracking procedure that basically starts without any correction and assumes that the distortion is smooth. But this will at least allow us to basically find seeds of the tracks and follow them a bit. And then we can extrapolate to the beamline and assume that they are primary particles or match them to other detectors. And by that, we can basically get the Z coordinate of the hit, and then we can apply the full correction and do a refit.
David, how contextual or how static are those distortions? Are they subject to changing during a run, or is it such that once you have the set coordinate, you're fine?
The distortions fluctuate. So there's two reasons for the fluctuation. So one is that they scale linearly with the luminosity or the occupancy in the TPC, so it just was interaction rate in the LHC. But that is basically a slow changing thing that we can correct for that by just measuring the luminosity with some fast interaction trigger and then scale the correction by that. The second fluctuation comes basically from the event structure themselves. So it comes from the band structure of the LHC, from the centrality of the collisions, from the event plane and stuff like that.
Yeah.
And this is short-term fluctuations that we have to correct for them. Say on the corrections need to be on the order of 5 milliseconds. So for each 5 millisecond interval, we have to create a new transform correction map. And this we do by means of this integration of the digital currents, because the track-based correction will not be fast enough to do that. That's why we have this
right.
mixed procedure.
So to summarize, at the as you said, at the very beginning, like in the very first moment, you don't use track information to do the correction because it's not fast enough. But then you apply them later on in a second calibration loop, or
yeah, I mean, what we can do at the beginning, basically, we can compute what is the average distortion for the current luminosity.
Understood.
Just
yeah.
that.
Understood. Yeah.
And that will be basically all we can do for the synchronous data taking. And then this correcting the fluctuations on this 5 millisecond level, this we can only do in the asynchronous processing.
Understood. That makes sense. Yeah. Thank you.
Okay, thank you. I don't see any other last chance for question for David. I see none. Okay, thank you, David.
You're welcome.
Next slide. Next slide is from Dejan Golubovic.
Hello, can you hear me?
Yes, we can hear you very well.
Okay, great. Okay.
Here's the slide.
So, okay, my name is Dan, and in our presentation, we have discussed CMS scouting. So the idea of scouting is to analyze events at the bunch crossing rate at much higher rate than possible with the trigger system. We have explored the use of deep learning to correct muon parameters to be as close as possible to offline reconstructed values. We have discussed our training and evaluation data sets and metrics, and talked about our neural network architecture and how we selected the best models. And then we showed the improvement we got on invariant mass resolution compared to the global muon trigger outputs. And then in the end, we ran our models on low inference hardware, and we evaluated that performance. So yeah, that sums it up.
Okay, many thanks.
Thank you.
Questions to Dejan? Okay, I have one. For these events which you analyze and throw away, what is the size, the ratio of the size between a normal event which you keep and this event which you analyze and throw away? What's the ratio of the size which is kept compared to the normal event? Is it 1/10 or 100?
I'm sorry, we did not select events to throw out or to keep. This wasn't what we were doing with the neural network. We were only correcting these outputs, phi, eta, and pt. We were doing regression. Okay. Maybe I didn't understand the question, sorry.
No, it's me. We didn't understand the talks. Don't worry.
Yeah, we will get the actual value of the measures in the end, not yes or no.
David, I think that the answer to your question is this is not scouting in the sense of DHSD scouting is done at level 1, and so events are not kept, they're analyzed on the fly. So the ultimate goal is to run the analysis on the fly.
Then you're filling histograms on the fly. That's what you're doing.
Exactly.
Okay. And also there is the entity. There's not even a few feature entity of the event which is kept.
No, because this happens within the level 1. There is no data acquisition. There is no event reconstruction. It's really the level 1 view of the event processed and extract information from it with advanced real-time analysis. Basically, the idea is to have, I think it's described in the level 1 TDR for the upgrade.
Okay. Andreas.
Yes, I have a question to the plot. If I don't really fully understand the plot, to be honest, so probably you can fill me in there. So why do I in the global? I need to move the window to see that. In the global muon trigger, it seems to be like it's practically blind towards shape psi. Do I see this correctly?
Yes. This is the main improvement we got.
Yes, but is there any? It doesn't sound like intuitive for me how you can.
There is no tracking here. This is done with level 1 muons. There is no inner tracking.
Right, but you would have a mu plus mu minus, right, shape psi, and you catch the.
Yeah, but the peak is very narrow. The resolution is so big to start with that you cannot see it.
So it's the narrowness that
Yeah.
that does this. Understood. That explains why the epsilon and the phi would be sensitive to that.
Yeah, at least for instance in the upsilons you see a big broad band for all of them together.
Yeah. Okay.
I don't see more raised hands. Okay. Thanks, Dejan.
Thank you very much.
Thanks to you. We're moving to the next speaker, who is Lucas. Lucas, I'm sharing your slide. Hi, Lucas.
Yes. So, yeah, very briefly, I'm going to discuss about the novel reconstruction algorithm for an imaging calorimeter, like the HGCal calorimeter that will be installed in CMS for the high lumen LHC. So this type of calorimeters with very finely granular longitudinal and lateral segmentation and also timing provide a very rich set of information. So there's lots of room for innovation, but of course there are big challenges that we're going to face at HLHC, like PyLab, combinatorics, also computing resources. So to this end, we are developing the iterative clustering framework, in short, TICL.
Hold on. Do people see the slide?
Yes,
I do.
Okay. Sorry. Continue.
I'm not sharing, right?
No, I am your slide. Yeah, but I'm struggling a bit. Okay, please.
Yeah. So yeah, to this end, we are developing the iterative clustering framework, in short, TICL. So as you will see as you've seen on the top right picture, this is a very modular framework, and the goal is, of course, to fully exploit the HGCal potential, starting from the energy deposited by particles, so what we call rec hits, and in turn particle properties and probabilities. Now, I don't have time to go over all these components, but the main components for TICL is the clustering step. So we group together rec hits and form 2D clusters. So we group together rec hits in the same layer and for the 2D clusters. Here we use the CLUE algorithm. I have a reference to the algorithm in the main talk, and is using the concept of local energy density. And then, of course, the other big part is the pattern recognition step. So there you link together 2D clusters to reconstruct the particle. And this is the pattern recognition is based on the Selgren automaton. One important thing is that both CLUE and TICL are designed to be GPU friendly, so they are suitable for the upcoming era of heterogeneous computing. Yep. And here I saw on the bottom plot, the bottom two plots are the performance in EM hours. So these are actually single photon events in the center of HGCal and no PyLab. On the left is the energy response, on the right is the energy resolution. And in order to understand the performance after each step of the reconstruction chain, we compare the reconstructible energy. This is with black marker. This is the energy deposit from the particle itself, the generated particle. The magenta color is the clustered energy. So we see that actually we can cluster almost all deposited energy. And the blue one is the tickle, which contains a large fraction of the clustered energy. So this is the response and can reach something like 90% for GeV photons. And on the right is the relative energy resolution as a function of the PT of the generated photon. And here we see that actually the performance is pretty good. It's pretty consistent with, in some sense, the ideal case, which is the reconstructible energy, the black markers. And we achieve a constant per term of less than 1%. Stochastic term is 25% or better. And one small comment here, that if we let's say focus on events that they don't, like we veto late showering photons, so photons that they don't leave energy after the EM section of the GCAL, this constant term improves down to better than 0.6%. We don't include the noise term here because from studies we did, then the effect is negligible. So that's all. It was too much. Sure. Protection.
Did we lose David?
Yeah, hi David.
Did we lose David?
Yeah, that's what I was wondering.
No, he's muted.
Sorry, yes, I'm there.
There we go.
Yeah, sorry. I was, okay, please activate your camera when you're speaking. For some reason with Zoom, as soon as I start sharing my screen, I don't see anyone else. So that's a bit struggling a bit.
Okay. Shall I start my video now, you say? Or
yeah, please, yes, please enable your video so that we can see see people. That's what we, if possible, if there is no problem with that of any other. So any questions to Lucas?
I had one. You talked a lot about sort of pilot zero. What can you tell us about how things scale up to sort of HLHC pilot levels?
So this is kind of active R&D. So we tried some simple methods and they look very promising. And one method we tried is the soft killer. So effectively removes, let's say, soft particles. This is a very promising approach, but of course there one can do even much more fancy things, and we are working on exploring machine learning techniques to improve the performance. But as you know, as far as we can tell up now, even with a simpler technique, this gives very promising results. So the response and the resolution is not very different from what we have in the ideal case, and there is lots of room for improvement there.
Okay. Any other questions to Lucas? Okay, and thank you.
Thank you.
Is Daniel Murnane able to speak now?
Sure.
Okay, so I'll share your slide. So sorry for the
Did he freeze or did I freeze?
I think we lost David. Froze again, I guess.
Bring bad luck. I'm not surprised.
And it's not muted this time.
Maybe somebody else can share the slide deck since David posted it.
I will. It'll take me a second.
I would, but I'm having breakfast, so I can't do it.
Oh, I can do it. I can do it. Sorry.
Okay.
Yeah, my son tripped on on the internet cable, so yeah. Can you see the slide now?
Yes.
Okay, so
Okay.
Daniel, please.
Thanks for being flexible. I hate to be that guy, but that's
No, you're not of at all.
So at the Exatrix collaboration, we are working on using machine learning for tracking at exascale. And at Berkeley in particular, we've been looking at developing a fast pipeline that takes TrackML data and produces either sets of seeds for traditional techniques to then do track finding and track fitting, or using some clustering techniques to get full end-to-end tracking. So you can see that we take in embedded data. So you can look at Nick Choma's talk for that. And then we create graphs and run those graphs through attention message passing networks, graph neural networks, and get quite good performance. And then we take that set of graphs and convert it into triplet graphs. And because we're using these scores and the information from the first GNN, we expect the performance to be even better, and it is. It's high. It's in 99% for purity and efficiency. So we can just apply cuts to those triplets and get very pure sets of seeds for traditional techniques with reasonably high efficiency at high PT. Or we are now experimenting with using some clustering, for example, DB scan on those graphs to get quite good performance of a TrackML score as well. And we see that the DB scan scales in quite an interesting way when you scale efficiency or purity. So it's early days with the DB scan clustering, but we're aiming to improve that. That's all I'll say.
Okay. Questions to Daniel?
So, David, I have a question.
Yeah.
Question and comment. As I said, that with the latest ACTS rollout, we'll have the TrackML writer available basically as a core component with a little tweaking. So how long? What's your turnaround time if I give you an entirely different detector but the same data set? Yeah, like, do you have to turn knobs? Do you have to go and okay, the segmentation here we need to differently. So how automated is your adaptation to a different detector?
The only thing that needs to be done is to retrain the learned embedding, the metric space, but the hyperparameter tuning there is very minimal. I mean, it's kind of orders of magnitude, and you get similar performance. So I don't think any knobs need to be twiddled with the metric learning. It would just require relearning that detector.
But also the field, for instance. Like, think about it. I'd be able potentially in a rather short time to give you Atlas data, Atlas lookalike data, or CMS lookalike data, where you have different fields, different setups. That's what I'm interested in.
I mean, like, that would be fantastic once that's available. I think the turnaround is very quick because, okay, each model needs to be retrained. That's the main limitation to fast turnaround. But the training is of comparable time to inference. So I think I have on the slide, inference is a couple of seconds. Training is order 10 seconds or less for each event. So you can train the entire pipeline within a day. Yeah.
Very nice. So I think we'll have to follow that up. We'll at least have a few either test detectors or reality-inspired detectors, let's call it that way, for testing. Because I think the interesting part of having an either supervised or non-supervised machine learning approach is also how transferable is the algorithm to within the spread of detectors, yeah. And of course it gets kind of I have to say it gets a bit more radical if suddenly that would be not a cylindrical central collision detector, but something like a forward detector. You know, there you start stretching the system. But I think that is an interesting question in terms of algorithmic understanding.
For sure. I mean, our next step, or even the step this week, ideally, is to look at the NCAPs of this detector. So I don't think it's a stretch to go to non-cylindrical. I thought your question was whether the actual same models, I mean, when the model weights, the trained weights could apply to a different detector. I don't think that's true. They would have to be retrained, but the actual algorithm is exactly the same. I mean, there's no geometric information in the pipeline.
Yeah, probably I add one sentence just to stress out my point that I wanted to make. In the phase 2 of TrackML, the winner did an order of 10,000 parameter optimization. Semi-automated, whatever that means. Now, we know that our reconstruction software throughout our detectors is highly tuned, and a lot of it is hand-tuned by experts that have been working on it 15, 20 years ago, or are still working if you're lucky. So having something more automated within the field, I think is from my point of view, also the way to go in the future. Yeah.
Yeah, that's a good point.
Okay, I think we have to move on. So this was our, hold on, first batch of speakers. There is something I'm reminded that we should have a, how does it work? I was not there when this happened, to have a group photo of this first batch of speaker. How did you do it, Andreas?
We just we ask every participant to switch on the camera, and then you get this massive grid. But it sometimes is even on 2 pages, and then you make a screenshot. I'm happy to do a screenshot. We could do.
And so when do you do this? Now?
Whenever you call it, yeah. Now let's do it now. But when we need to ask everyone to switch on the camera, if they want, it's not compulsory. As in a conference, you're not. Well, no one is dragged to
the go photo. Okay, everyone.
David, you need to stop sharing your screen, otherwise
I need to stop sharing my screen. Absolutely. One more month of this, and I would be completely fluent with all these tools. Arrêtez de partager, voilà.
Yeah.
Okay, so everyone, please activate your camera. But now,
David, do you mean everyone or just from the first batch?
No, everyone.
Everyone. We're learning while walking.
We decided to if we want to have an overall photo, we're gonna do some Photoshop skills or whatever.
But I only see a band of
okay,
people.
I have the grid view.
The grid. I have the grid as well. Okay.
Yeah.
So. Continue, David Lange. You are there at least one time.
Here we go.
Sebastian, it's quite nice.
Yes.
Let's see the second page.
Second page, yeah.
Sabrina, you can activate your camera if you can. Erika, Xiao. Hello, Sabrina.
I have a problem with the camera.
Yeah, sorry.
You don't have to, and it will be very strange that on the 40 people that some fraction has some problem of camera. Or...
Don't worry, David. I think we'll sort that out later on. Okay.
Okay. No, the success rate is quite high. Okay. I'm taking a few pictures and I'm going to do something about it.
Really good. Cheers.
Okay, this worked quite well.
Yes,
Okay,
thanks everyone.
Okay, so you can switch off your camera. Good. And then I have to restart the sharing. I think that every community has a different tool, and in different community I'm using Teams, and now I'm fluent in Teams. You have to learn Teams, Microsoft, yeah, Zoom, and whatever. Okay, let's go back to share my screen. I'm sharing this one. Okay. And now we'll go to the second batch. So Pavel is next. Pavel, you were there. Let me show your slide. Pavel, yes, please, Pavel.
Yes. Hey, David. Hi, everybody. Okay, so let me, okay, I'm not seeing actually the slides shared, but...
can you see my slides?
I'm still seeing you.
Yeah, yes, voila.
Right. Okay, that's perfect now. Yeah, okay, thank you. Yeah, just a quick reminder of what I said. So it was about the connection between the least squares, we call it global chi-square alignment, and the Kalman fitted tracks. So as a reminder, the global chi-square approach to the alignment results in a big system of linear equations, which is indicated on the top of the slide. So there's the matrix, which actually contains all the features of the solution, so to say. And the inverse of the matrix is basically the covariance of the alignment parameters that we want to solve for. The central object in this in the equation actually is the full covariance of the residuals of the track fit. What is meant by full? It's basically their intrinsic covariance plus the bit which comes from the track itself. So that's the R object, which is V minus the HC. HC is the covariance of track, and the H are the corresponding derivatives, which are indicated further down. So it's just the derivative of the residual with respect to track parameters. So now to Kalman filter track model, which well consists of actually states on successive surfaces. And the track is defined by the well, track parameters, usually 5 parameters per each surface. The covariance which you construct during well, Kalman filter, which consists basically of 2 stages: the forward filtering and the back smoothing. Returns you the diagonal elements of this C matrix, so the covariance. Why I'm talking about it? Because actually for the alignment purpose, this covariance matrix and effectively this R object is absolutely key and basically central for having. It's just giving you the correlation between the measurements, which is your gauge for alignment. That's the whole point. So of course, the problem that arises is that you have only these diagonal elements. You don't have off-diagonal elements, which are still very important or crucial for performing the alignment. However, these off-diagonal elements of C can be obtained recursively using the already known or obtained during the smoothing process smoother gain matrix, which is defined here. Actually, looking carefully at the algebra, it turns out the calculation of R in case of Kalman filter tracks, as opposed to least squares fitted, so the chi-square fitted tracks, is relatively fast, thanks to the sparse nature of the derivative matrix H. Further on, constraints on track parameters, which are very important for the successful alignment, can be introduced just as it is done in the least squares approach by adding pseudo measurements on the track in the filtering process, and in case of Kalman filter, it's basically equivalent to giving some meaningful prior to start the filtering. Also, any other constraints like vertex, invariant mass of the resonance, etc., can be equally introduced with full propagation to Kalman states which do not involve large matrix inversion. So basically, the conclusion is that you can equivalently use Kalman filter tracks for the global chi-square alignment, and it appears even computationally often less intense and more straightforward than in case of least squares fitted tracks. Yeah, that's it.
Thank you. Okay, question to Pavel. I have one side question, but
yeah.
There is a more direct one.
So honestly, I have to say I didn't listen to your talk in the recording session on YouTube, but so just looking at this, I mean, I know that in LHCb a Kalman filter tracks is used for an alignment. So I just looking at this slide, I'm not quite sure what you compare this to a least squares, and you conclude that you can use Kalman fitted tracks for alignment, or is there anything beyond the usual Kalman approach that you discussed? So
okay.
It's confusing. I should look at your full talk, I realize.
No, okay, that's fine. No, you're right, absolutely. Actually, as I indicated on the first slide of my talk, the experience of LHCb and also I listed all the relevant input and the earlier papers were essential for essentially my very short review. It's nothing really completely novel. It's well known, at least in LHCb, as you rightly pointed. It has been used, and it's just the fact that in some other experiments, for instance, like in our case in Atlas, we haven't done yet the switch, so we have been so far using the least squares track model for alignment specifically. However, what I did in the talk, which is not actually maybe visible here, is I mostly tried to compare the cost, the computing cost for the two cases. That's one thing. And I also gave some, for pedagogical purposes, very, very simple examples where basically on back of an envelope or really you can see the equivalence of the two approaches, and you see where they differ computationally and why they end up being completely equivalent at the end. So yeah, you're absolutely right. It's not a discovery of anything. These are well-known facts. However, I just wanted to give more proper insight into how it works.
Yeah. Quick answer for a quick question, side question. Nowadays, people are people considering using TensorFlow for all the matrix multiplication, well, the manipulation which is done in all these element business? Has anyone looked into it using TensorFlow?
Well, not that I know of in our case. I don't know honestly if there are you know
the more
yeah.
aggressive question probably, David, is did anyone look into AutoDiff?
I mean the new way, all this technology, which is a kind of spin-off from all the machine learning optimization world.
Yes, but yeah, okay. Of course, all I'm talking about has still nothing to do with machine learning, okay? Which is of course.
No, I'm looking at machine learning, but TensorFlow is minimization, well, matrix optimization, manipulation package, and people have started to use it to do stuff which have nothing to do with machine learning.
Okay, so but fine. So probably the answer to your question is that this is a kind of a completely different aspect of alignment, yeah, which is the how to deal best or optimally with solving the big system of equations.
Yeah, exactly.
I think this is basically what you're asking for.
Yes.
So of course this is a different question. All I was talking about is essentially this step before, which is to get to the system of equations.
It was a side question. I'm sorry, Pavel, we have to move on because there are a number of talks to go through. Many thanks.
You're welcome. Thank you.
Next speaker is Sebastian Cambrax, whom I didn't see the slide. Is he online, Sebastian? Yeah. No, I don't see him. Then we move to the next speaker, who is Federico Lazzari.
Yes.
Okay, you're there. Your slide is shared.
My microphone was muted. Okay. Sorry. You can go.
Yeah. Yes, you can go, please.
No, the talk was about the optical network for the artificial retina, a tracking system that can operate at the very first level of processing. The distribution network allows us to collect data from several DAQ nodes and overcome FPGA size limit, placing the tracking cell over separate chips connected together with optical serial link. The system can be integrated in LSCP data flow, and we studied the velo tracking. That is an interesting case of study. The simulation show very close efficiency performance, and we tested a life-size. We have a life-size prototype of 10 boards in advanced state of realization, and we performed a long-run test at max speed on a smaller version with no transmission error detected. The plan is to perform the realistic parasitic operation during run 3 data taking. This was.
Thank you. Any questions? Federico. To be honest, I was confused by your talk because it's optical network and then there is artificial retina. So there is two separate things. So you have an artificial retina and you're using optical serial links.
Yeah,
so,
inside the architecture of the artificial retina is explicitly described the distribution network. But since there are more DAQ boards and more tracking boards, we need to collect them with some high-speed link, and the optical serial link are the best solution.
Okay. Any questions?
I had one. I think maybe this came up in your talk, but can you see how this interacts with, especially if you end up with a GPU-only trigger, first level trigger effectively, how does this interact with that?
This is a tracking system that can run before the event building. So if the full tracking and the full event reconstruction is performed by GPU, is not something that conflict with us. We can provide to the GPUs tracks or proto tracks before the it's. So the GPUs can avoid to reconstruct tracks of some subdetector, of the most complicated subdetector, and perform maybe a full Kalman filter or more sophisticated operation. This is a pre-processing step, and then you can do what you want with CPU or GPUs or other kind of heterogeneous calculus.
And it's part of, just to understand, it's part of the, I'll call it baseline. When we see a talk from, like we had a talk from the Allen project or the similar for the CPU, is it part, this pre-processing is part of their baseline, or it's separate?
No, it's not a baseline. We planned to perform a parasitic operation. So during run 3, we have a system that steal data from LCB and perform the tracking, but without using it in the mainline sequence. If the parasitic operation will be successful, we can think to implement a baseline tracking system for round 4 or round 5. For round 4, we are planning to perform the tracking of the downstream tracks, that is the tracks without hits in the velo. And so they are quite complicated to be performed because the hits can be spread over a great area.
Okay, thank you. That helps me.
Okay, thank you. We move to the next speaker, who is Sebastian Schlag. I think he's online.
Yes. My microphone was just muted before.
I
guess. Okay. Can you hear me now?
Yes, we can hear you.
Okay. Okay. Yeah, then you say the order.
So who should start? Sebastian or me?
Okay. I have some. Whoever is it, Sebastian?
These are my slides now.
This slide is your slide. Okay, please click now, and who are you? I cannot see you. This is Sebastian.
Sebastian.
Yes, this is Sebastian. Sebastian's slide. Yes. Okay. Okay.
I think we just skipped over Sebastian because his slides weren't there.
Yes, exactly.
No, my slides are online.
Yeah. Okay. Let's go first to Bastian Schlag.
All right. Okay. Thanks. Okay. So my talk was about ACTS vertexing and some current developments in the direction of deep learning vertex finding. So in ACTS, we now have fully functional MT-capable vertexing suite, which is written in modern C++, has been numerically validated with respect to the original Atlas implementations, and also shows some significant speed up with respect to these implementations. In terms of ongoing developments in ACTS, vertexing developments, we are currently working on a vertex seed finder that is based on a Gaussian track density, which shows comparable physics performance with respect to the original continuous density track density seed finder version implemented in Atlas, but shows a speed up of a factor of roughly 35 for high track multiplicities, as you can see on the right hand side. So it makes it especially suitable for high pileup events. And another ongoing development I talked about was a Siamese neural network vertex finder approach, where we take a neural network to predict a score that two tracks come from the same vertex, and with these scores we can then construct graphs where the nodes represent tracks and the edges represents these scores, these similarity scores, and then we have these graphs that we can cluster to subgraphs, which we would then identify as vertices. Yeah, thanks.
Thanks, Bastian. Question to Bastian? Raise your hand or speak directly. It's not like we have many of them. I have a question. So what are exactly, you give parameters for each track, right? And what...
you're talking about the neural network?
Yes.
Well, okay, so the idea here is basically that we want to have a network that is able to find a track embedding or track representation in some embedding space in such a way that we take the track parameters plus the flattened covariance matrix as an input, and then we want to have a neural network that predicts a track representation in some embedding space in such a way that tracks that are similar in such a way that they come from the same vertex are close in this embedding space. And then we always give as an input a pair of tracks to the Siamese neural network, which then can predict this the score.
Okay, and then the clustering into vertices. How do you go from the pair of track to the cluster?
So what you can do is you just, for example, I mean, you take your entire track collection of your event and just order all these tracks in the set zero value, and then you would just define. So this is really ongoing development and far from being completed or whatever, right? So this is really only the first steps in this direction. But what you can do, or what I did so far, was basically I defined a certain set zero window, and then within this set zero window, I would create all the track pairs and just predict all the similarity scores. And then, of course, if you have a track pair and the score in between, you can see it on the lower right hand side. This graph example. You have two tracks and the similarity score, and then you do it for basically every combination within your set window, and out of this you can then construct this graph representation.
Okay. Thanks. I think we have to move on. So now we move to Sebastian Cambrax. So can you please share your slide, because I didn't manage to do it. So I'm stopping my sharing.
Okay, can you see it now?
Yeah, yes, perfect.
Okay. So this is about the 3D track trigger we are developing for BEL2. The main component is a neural network trigger. And with this trigger, we like to trim away tracks not pointing to the IP and make, for example, a cut at plus minus 20 centimeter. And this neural network trigger tray takes single tracks as input and the track segments for 9 super layers in the CDC. Each is encoded with 3 values, and this is already implemented in hardware. With this, we get like 4.3 centimeter resolution in the first debug results in hardware. But this neural network trigger now depends on it only works on found tracks, so we like to improve the track finder before. The present 2D finder only uses the axial track segments, and we like in addition to use the stereo track segments. This is done by, in principle, patching together 2D half planes to a 3D half plane and training the patterns in this half train from a Monte Carlo data set. And with this method, we get an efficiency improvement, as you can see on the right in this initial state radiation events. There we have in the low PT region and for flat theta angles, an improvement of about 1.5, factor 1.5. And the neural network can correctly process the additionally found tracks by the 3D track finder, which can be seen in the plot below. And yeah, for 2-track events, for example, in this pi plus pi minus final state, we get 98% efficiency with this neural network trigger cut. Okay, yeah, this was a quick summary of the talk.
Okay, many thanks. Any questions to Sebastian?
I have a question, if you can.
Yes, please.
Gian Antonio. Very nice slides. And yeah, I actually was curious. Can you please comment on the top left plot, the bumps which are present in that distribution? This is from data or is from simulation?
Yeah, this is early Bale 2 data, and yeah, this is definitely background. The plot is created with the offline reconstruction, so we know precisely where the tracks are coming from. And yeah, this is the background distribution. This is caused by regions with heavy material where we have lots of backscattering tracks that yeah, hit the detector. And this yeah, is far away from the IP, so it's in centimeter, and where I have marked this in red is like plus minus 20 centimeter. This would be a good region to cut away this background, and this can be done with a neural network.
Okay, thank you.
Thank you. Any other questions? I don't see any. So thanks a lot, Sebastian. Please stop sharing.
Okay.
And next is Will Calderon. You have also uploaded your slide, but please share your slide yourself.
Okay.
Yes, perfect.
Okay. Great. Well, you can see me. Why not? So yeah, this my talk was about 2 algorithms that might help with some high rate tracking in Atlas. It's going to be well, because tracking is very important for performant triggers, especially in the HLWC, is very high piled up. And so the 2 algorithms. Oh, right. Zoom just told me screen sharing stopped unexpectedly. That's nice that it notices. Okay, should be back.
Yes.
So the Hofstrasse, well, it was mentioned in the previous summary, but right, the idea there is you map hits to possible circles, and therefore you find coarse estimates of track parameters just by finding maxima in 2D histograms. So that can be quite fast. But it becomes less efficient at high impact parameter, right? Because you're suddenly have to increase the parameter space of circles you're willing to search for, and it gets less efficient, or it requires a large increase in the amount of computation you have to do in order to get the same efficiency. So then another approach is stub finding, which is actually designed into the CMS detector, and so thought be useful, interesting to look at for Atlas. And the idea here is it uses the angular displacement between back-to-back modules to reject low PT hits. So a little sketch there. High PT track goes through pretty much straight, but there'll be a larger shift in phi for a low PT track that's more curved. And so you can use that then to discriminate low PT hit pairs and therefore reject stuff really just based on back-to-back layers like that. And it's less sensitive to the impact parameter. And so the idea of doing that is that you could maybe reject hits earlier, and you could maybe, for instance, then feed the surviving hits through to a Hof transform and increase the impact parameters that you can be sensitive to, or things along that line, or maybe have it instead feed it to precision tracking and run more precision tracking because you're feeding it less hits, and there's less, therefore less combinatorics to build tracklets. And so what I presented was just some predictions based on the Atlas upgrade tracker, the ITK tracker, based on the layout of that and the script text that we actually have, and well, not that we have, that we will have. And it looks fairly promising. We don't get the CMS. Remember, CMS for 2 GB tracks can reject about 90% of low-PT tracks, I think they said in their TDR. What I find is a bit less than that, but still a reasonably substantial amount of rejection. And so what we're doing now is trying to propagate that to track efficiencies, because that's what matters a bit more, but we don't have that quite yet. So.
Okay, many thanks. Any questions to Willem?
I have a question, if I can. It's Jonathan
Yes,
again.
please.
Sorry. Sorry, I'm trying to do it as much as I can. Yeah, very nice slides, and actually, it's really a curiosity. So, I guess that by using the off transformation, then you're limiting yourself for not on actually looking for tracks coming from the interaction point, right? So, I was wondering, like, do you have any guess of the performance for tracks with displaced vertices, which are not?
Yeah. So if it's quite tunable. So if you look at my original presentation, I have some plots there that a study was done on a kind of toy detector that it more or less the effect is worse at low PT, and you can play around quite a lot with the size of Binet and Hoff transform and what size intersection you're willing to tolerate. So I can't give a particular number on it, but yes, it does degrade quite a lot. But if you want to see some plots of it, then if you click through, and somewhere in the middle of the talk, there are some plots showing 2 different configurations of the efficiency versus versus D0.
Okay, thank you so much.
Okay, thank you. I don't see any other raised hand. Okay, thanks a lot, Will. So the next, next batch of speakers are Jeremy Hughes, François Drielsma twice, and Yutaro Liyama. Jeremy, you will share your slides, and for the next 3, I will share the slides. Please. So Jeremy, you can...
Just about missed the boat.
Perfect.
Uploading.
Yes, you can see them.
Okay, fantastic. Well, so I presented a talk which is part of the Xtrix collaboration and kind of builds on talks by Daniel, Nicholas earlier, which takes some of the concepts that have been shown to work really well in the LHC for applying graph neural networks to tracking, and try and apply those to a different problem, which is reconstructing neutrino interactions in liquid argon time projection chambers, which are a detector that are very heavily used right now and will be more heavily used in the future when Dune turns on in 5 years or so. And so I've been exploring a couple of different approaches to do this. I think one of the big takeaways from my talk was I haven't found a configuration that works really well yet, specifically in 3D. So the first thing that I tried was taking the message passing network attention and residuals that Heptrix used and trying to apply it in 3D for things like clustering 3D space points together and removing noisy space points. I found that the network that they use in the LHC doesn't really translate well to a dense 3D point cloud. I also tried some networks which are more natively designed for 3D point clouds, but instead there I found there was a computational bottleneck where some of the operations they do aren't very well optimized for really large graphs. And so I wasn't really able to find anything that worked well in 3D. So we're looking at 2D now, which I have a kind of an example of event display in the bottom left of drawing potential edges, within a huge electromagnetic shower, kind of drawing the lines to connect all of the individual subparticles within that shower. And I think this is an approach that conceptually is a lot closer to the kind of problems that the Heptrix collaboration found to work really well. So you can leverage the kind of physical configuration of your detector to cut down on the number of edges. And so we're in the process of testing that approach now, and we'll see how that performs. That's kind of the summary of my talk.
Thank you. Questions, Jeremy? So maybe comment or question. Yeah, so clearly in this case of the RTPC, you have a lot much more points, well, virtual points than at the LHC. I mean, for each event, but then you only have. It's not like you have 10,000 tracks. You only have these weird. You have the shower, which is
right.
a very different object with a blurb of. Yeah, so
that's exactly right. So I think the big takeaway that I had from these early studies is very much realizing the ways in which the approaches that work well for the LHC don't necessarily translate, and needing to figure out how to structure your data in such a way that it actually works well. Right.
Okay. Any other questions to Jeremy? Oh, okay, thank you. Yes, please stop sharing. And now I will share my slide. Partager l'écran. So please activate your video when you're talking. François Drielsma, this is the one on the ML Reco chain for RTPC.
Hello, can you hear me?
Yes.
Okay, thank you for joining. So I'm just going to give a quick summary of the talk I gave last week. The idea here is to have a end-to-end machine learning-based reconstruction chain for liquid argon TPCs. And if you are not familiar with the kind of images we're getting in RTPCs, there's an example on this slide. So if you just look at any of the image, you can see we've got a bunch of tracks and showers in the detector. And we are trying to extract information out of these images. And the way that we propose to do this is to have a hierarchical feature extractor. So we use different machine algorithms to extract information out of the image. And what we start with typically is to use a UResNet type architecture to extract dense features. So first the particle type, and here I'm giving you a performance metrics for each of the stages. So if you just look at the performance metrics, we're trying to predict particle types. So it's basically classifying voxel-wise where each of the voxel belongs to a shower, a track, etc. And you can see that this using machine learning performs very well. On average 99% accuracy. Then we try to predict interesting points in the image. So you're trying to predict the endpoints of tracks, for instance, and the start point of showers. And you can see this plot, it's hard to read the axis, but essentially it's a distribution of the distance between the predicted points and the true points that we put in the labels. And you can see, if you can see at the axis, is that typically the network predicts points that are closer than one voxel away from the label points. And typically the efficiency of this algorithm, which is how many times do we have a voxel that's less than 10 voxel away from the label point, is 97% roughly, and purity equivalently is close. And then the last thing we do using the UResNet is to try to fragment our image. So we try to separate the different tracks into different instances. And we also try to predict different shower fragments into separate instances. This also works really well using a UResNet type architecture. And at this point, what we have is a bunch of detached shower objects. And so CNNs are not really appropriate to do clustering at this stage. And so we move to using GNNs at this stage in the reconstruction to try to put the different shower fragments together. And you can see that actually using GNN for this works well. Here I'm giving you some clustering metrics. And finally, the last step of the reconstruction is trying to put different particle instances together. So now we've got shower instances and track instances coming from the previous stage. And we want to put together into neutrino interaction, so which is typically the kind of thing we are trying to reconstruct. And so using, again, GNN to do this task works well. Typically, the density we expect for this image I'm showing is roughly 2 neutrino interactions. So this is why I've highlighted the performance number for 2 neutrino in this example.
Thank you. Questions to François? Actually, for Dune reconstruction, I've only seen heard talk using machine learning. Is there any baseline traditional combinatorial reconstruction to compare with?
So there is, yes, which is called the Pandora framework, which only uses, well, actually it's starting to implement different machine learning technique into it, but it has some non-machine learning technique remaining, such as cone clustering for showers, etc.
And how do you compare to this technique?
Well, so I don't have an exact comparison here, so I'm not going to quote numbers, but typically machine learning performs better, at least, than traditional programming.
Okay. Okay. Any questions to François? Okay, thank you. So see you in 5 minutes. So next is Yutaro Liyama. So I have your slide now up.
Hi, thank you. This is actually Iyama, my last name. It's 2 eyes.
I'm sorry.
Yeah, it's okay.
Whole bunch in one
No.
day. Sorry. Please go ahead.
Neural networks for FPGAs. So implementing a graph neural network on an FPGA. So we first identified the, do you hear me? This is, yes, my internet connection is unstable. Okay, good. We identified the key challenges for implementing the graph neural networks in FPGAs, which are basically just the sheer number of operations. So many multiplications you have to do, given the depth of typical GNN architectures. And also memory capacity and the axis pattern, because when you have these like list of edges, you would dynamically be accessing vertices from a list of vertices, you know, like different elements of vertices serially. So that doesn't really, it is not very FPGA friendly. So there is one algorithm, Garnet, that we developed, which addresses these issues. Firstly, because it doesn't have any edges in the input, so it reduces RAM usage, obviously, but also it regularizes the memory axis, as I said, because edges are the part that creates this random memory access. And then also it has non-linearity in edge weights, edge being here a connection between vertices and virtual aggregator nodes that are sort of embedded in the architecture. And this non-linearity helps to make the other parts of the algorithm shallow. So the non-linearity is a graph neural network in Garnet. So we implement on the FPGA with further simplifications, and these simplification ideas were sort of presented in detail, and I think the ideas there could be applicable for other neural networks if they want to have an FPGA implementation. And also this Garnet HLS was the high-level synthesis was the language used to write this FPGA implementation. The Garnet HLS implementation is available in the HLS4ML framework, so it's sort of publicly usable. Actually, the pull request is not merged yet, but it'll be available very soon. And then finally, we presented a case study of this implementation with a toy 3D colorimeter simulation, and basically we did the classification and regression of electrons and pions simultaneously with this network, achieved sub-microsecond latency while having reasonable physics performance, which are shown in these 2 plots there. So yeah, that's the summary.
Okay. Many thanks, Yutaro. Questions?
I have one. This is Paolo. Sorry, I haven't read your slides yet, but I will certainly read them. So the question is, in your FPGA, how should I say, compression? Did you use things like reduced precision numbers? And if so, does it have any impact on training stability or performance or anything like that?
Right. Yeah, that's a good question. The precision. This HLS4ML framework does not use floating point, so everything is fixed point, and so we have to define what the precision would be. And for this Garnet implementation, we used minimum 10 binary digits for the fractional part. So basically 0.1% precision for all numbers. And but then because you asked about training, training for this is always done on CPUs and GPUs using Keras. HLS4ML allows you to train these networks and then convert that to, after training, you provide the weights as an output of the training and the model parameters, and you just convert those into an HLS implementation. So there's no training involved with these fixed.
Okay, understood. Is it? Yeah. Can I ask a follow-up, David?
Yes. Sure.
Is it? I mean, how are you sure that by zipping the network after the fact, you are actually not losing some potential performance? Because that some cases there is evidence where using reduced precision in the training is actually improving the performance compared with zipping after the fact.
That's possible, yes. We do lose performance somewhat, and it is actually shown in these slides. If you zoom in, each of the slides show Keras continuous, HLS continuous, Keras quantized, HLS quantized. I'll explain first two. Keras continuous and HLS continuous are, so Keras continuous is basically just a straight Keras result. So given this model, you run on GPU and train on GPU and then run the inference on GPU with floating point full precision and get the result. HLS continuous is the HLS version of that, and we using fixed point. So there is some difference, as you can see, but very minor in this particular study. In some cases, yes, the loss of performance is fairly substantial, but in the particular case study that we did, the difference was very minor.
Thank you. Yeah, I should have looked
at the quantized. Yeah, okay. Yeah, I think I shouldn't go too much in details. Yeah.
Okay. Okay. Thanks a lot, Yutaro. I think we have to move on.
Yep.
Next speaker is François again. Your slide is up.
Okay, thanks. So yes, hi again. So having a second slide allows me to go just a bit more into detail about how we do shower clustering. So just here, I want to stress that we don't do shower clustering in a single pass in a CNN because, as you know, we have far away detached elements in a shower, so it's difficult to do single pass clustering using a CNN. So we first cluster fragments together, and then we put them together using a GNN. So we extract features for each of the fragments, and we embed them as nodes in a graph. And then we do message passing in that graph. So we update the node features and the edge features sequentially, and we can repeat this process. And then we make inference on the edges. So we try to predict whether an edge is on or not, so whether or not it connects to nodes that are within the same shower. And from this edge prediction, we do the grouping for the showers. So this is what is shown on top here. And then using the node features, actually, we leverage that to try to predict the start of the shower. So what is the fragment that initiated the shower? And so on the bottom, I'm showing an example of the prediction we get out of the network trying to put the showers together. So you can see that the network predicts which are the most likely edges that put the shower together. And I'm showing also some metrics of the clustering. So the error is quite high, which is a stringent metric on clustering. And also I'm showing an example of what the network is predicted for the shower starts, which in this case is correct. And you can see that predicting the shower start is 98.5% accurate using this technique. So that's all I've got.
Thank you, François.
Thank you.
Questions to François? Yeah, I have a simple question. So typical for all what you're doing, what's the typical training time, and on what kind of machine are you doing the training?
So it depends on the task, but so if it is this particular task of the GNN, these networks are actually quite small. We can fit that on basically any commercial graphic card. This one typically is trained on a 2080, and it takes about 2 days to train, so it's quite fast. For the CNNs, it's a lot more complex. So we usually use V100, and it takes roughly a week typically to train.
Okay, that's already something a bit heavy, but okay.
Yeah.
How many parameters total?
That's I don't have an estimate of that. I haven't thought about that.
Okay.
Sorry.
Okay, but this thanks for the order of magnitude. This is useful. Any other questions to François? No. Okay. Thank you.
Sorry, just to comment on what you asked.
Yes.
So keep in mind that this is done once for training, but it's not done online and continuously.
Yeah.
So even if it takes a couple
I
of
understand, but it's never done once. It's never done once.
Yeah,
okay.
Of course.
But no, it was just a curiosity, and of course, yes, inference time is completely different. Yes.
Yeah, and comparing, I don't know, maybe Francois can comment on that, but at least in Microboon, which is I think my next talk, that comparing the time it takes for training to the time it takes to produce for production of data, that's not the longest part.
Okay. No, but it was just to have some idea whether you were doing this on your laptop in a few minutes, or you need to to wait more, or you need a supercomputer to do the training. So it seems to be in between.
Yes, I'm somewhere in between. That's right.
Okay. We move now to the last batch of talks. I have them all. So this is Han Itay, Bei Wang, Xiaokong Ai, and Panchali Nag. So first is Han Itay.
Yes, hi, thanks.
Hi.
So I've been talking about applying submanifold sparse CNNs in Microboon. And the idea is that the Microboon data can be represented by 2D images. If you represent it as 2D images, we can apply deep learning analysis for extracting neutrino interaction features. One of the first tasks is a semantic segmentation on the pixel level. The problem is that the data is very sparse. We have less than 1% of the pixels which are non-zero. And actually, if you take pixels above threshold or between thresholds, only 0.5% of the pixels are important. So working with just dense standard algebra is very inefficient. So the idea was to use a sparse submanifold convolution neural net. This improves dramatically the results. In terms of memory usage, we had to crop our image to about 60 images. If we used the standard algebra, now we can do without any cropping, and actually we can fit probably all the data on one GPU. It's about 1 gigabyte per full image. The improvement in the time is also great. It's about 2 seconds for a full image inference on CPU, where we don't have to optimize, quote unquote, our network for the CPU to accommodate it. The accuracy is really high, about 99%, and this is coming from the fact that in these networks, we don't allow pixels which were not activated at the input level to become activated at inner layers and hidden layers, sorry. And that means we're not losing the sparsity of the data. So we are not blurring the data to become, and which affects the quality of the inference. Also, this is scalable to 3D and bigger detectors, as Francois just presented. I've also plotted here the accuracy of the 5 label. This is the original task I'm doing. However, in the analysis itself, we're reducing that to 2 labels. If we look at the 2 labels, we see that it's above 99% accuracy. And then on the right, you can see some example of images which we're looking at. On the left is an example for something which we use for constraining our systematics, one mu1p interactions, and you can see the input is the top image and the output of the network is the bottom image, and you can see that the green pixels correspond to a muon and the blue ones correspond to proton. And on the right, you can see the signal that we're looking at, which is one electron, 1 proton. Again, the top part is the input and the bottom part is the network prediction. So yeah, that's it.
Thank you. question to run? I have one question. So in the case of microbone, the data is already 2D. You're not doing the projection just for your treatment, right?
Right. Yes. We have 3 wire planes, and each of them produces a 2D image. And the way we treat it is that each plane has its own sets of weights. There's no data that is shared between the planes. So at this stage, we share the data just in the later parts of the analysis.
I see.
So for example, trying to find the entire shower would be taking all 3 planes and projecting a cone in a way that will help us for that. But for this task, we use each plane, we treat it separately and train on each plane separately.
Okay, but there is no like I think Nova did attempt to join the 2 representation.
Not at this stage of the analysis. Okay. No, not at this stage.
Okay. I don't see any other recent hands. Okay, thanks a lot, Ran. Next is Bei Wang. Are you online?
Yeah, I'm here.
Okay.
Okay. This is a summary of the early talk. CMS is evaluating the use of GPU in the high-level trigger for round 3. And in order to include MK-FIT, the parallel common filter tracking code, into the workflow, we start to explore its GPU implementation. We start our work from unpacking and clustering. This part actually is currently done sequentially in CMSSW, and we in our work we develop a parallel clustering implementation by first converting the raw data format from CMS to structured array format. We also introduce multi-event processing to improve throughput, and on GPU this is done by using multiple GPU streams, which actually on one hand can maximize the GPU utilization, and on another hand reduce the overhead of overlapping the computation and communication. On P100 GPU, we can achieve up to 650 events per second throughput, and that's about 15% better than running it on 28 cores Broadwell. So the next step, we plan to integrate this standalone code to the CMSSW framework. And at the same time, we need to convert the cluster into the MK-FIT input format, that's global coordinates. As we explore the CUDA implementation for the GPU, we also start to investigate the OpenCL implementation for the FPGA. And ideally, we want to see that how is the performance looks like on a variety of platform, include CPU, GPU, and FPGA. And we have the code available in the GitHub, and we also have a wiki page at the GitHub, provide the optimization details for the code.
Thank you. Questions to Bei? Just precision. So on the performance results, the CPU is actually running on 28 cores in parallel. That's
right.
Okay.
Right. We use more the cores on a single node.
Okay. I see. So it's basically means that if you compare one core CPU with GPU, it's a factor, well, 24, which is quite a significant one. And did you have opportunity to analyze in the case of the GPU, what was the limiting factor?
The GPU, the limiting factor is, I think that on one side, when we actually use the unreproof to looking at the final performance result, we see that when running multiple events at the same time, that we still get a relatively big gap between one and another event. So that means we probably have something in the middle to maximize the overlapping of different events running at the same time, and we need to investigate that. That's one of the problems. And another problem is this piece of code is memory bounded, and so the bottleneck is in the GPU memory, and the most time-consuming part for our GPU implementation is on the unpacking part. That's because the unpacking involves the irregular memory access, and right now we don't have too much idea to optimize this part because it's more like the nature of the algorithm itself. You need to transform the raw data into the more favorable structure of array format, and so that's kind of one of the biggest limiting factor for the performance.
Interesting. Don't see any other right hands. Okay, thanks a lot, Bei. We move to the next speaker, who is Xiaokong AI.
Yeah, David, actually, could I share my screen because I have a little bit update to my slide.
Okay, so I need to unshare my screen. Okay, go ahead.
Okay, thank you. Okay, could you see my screen?
Yes, perfectly, yes. I think that's fine.
Yeah.
That's fine. You can see it.
Yeah, so my talk is tracking with ACTS. And as a tracking toolkit, ACTS has grown a lot in the past year. So there are a lot of consolidation of the tracking infrastructure, such as the geometry, the propagator, and the EDM. And there are also a lot of new tracking features implemented, such in particular, the cumulative kernel feature for the track finding and the vertex fitting and finding, as you heard from Bastian. And we have validated the performance of the tracking features, but some of them could still be optimized. For example, here, this is the performance of the ACTS CKF. So I updated this plot after using a tighter track selection cut and also fixing some bug in the code. So the updated efficiency, we have that above 98% in the barrel rating of the detector, and for the fake rate, it's below 10 times -4. And ACTS is also a very active R&D platform for not only the new tracking techniques, but also for the hardware architecture. So for example, here, this is the speed up of the ACTS seed finder on GPU. And in the scenario of the high luminosity LGC, we can have a factor of 14 speed up for the seed finder. In terms of the detector application, there are a lot of experiments involved and a new detector implemented in the past year, such as the Atlas detector and also the S-Phoenix and the BL2 detector. And some future perspective for the midterm, we are facilitating the detector application and the software framework integration, such as for the Atlas Run3 software. And the long-term goal is provide a full tracking solution for the future detector, such as the high luminosity for Atlas Run4. That's all.
Thank you. Thank you, Xiaokong. Questions? Okay. My question, I guess, is that you mentioned the speed up, but what is the absolute time on either CPU or GPU you obtain?
I don't remember the exact number, but so the speed up is the time of the CPU and over the time of the GPU. I think.
We're talking about 10 seconds, 1 second, 100 seconds per event?
I think it's a few seconds.
Okay,
yeah.
just to have an order of magnitude.
I have a question, if I may. I shot some.
Yeah.
I was wondering, and that's because I'm completely ignorant of how a CKF works or does not work. I was wondering why there is the drop at high eta. Is this because you are requiring 8 hits, or are you kind of unfolding that?
Sorry, the drop at where?
In your top plot, you show that you have very good efficiency in the barrel, but then the efficiency drops pretty quickly. And I was wondering what is the origin of that? Is the requirements of 8 hits or what?
It's because the requirement on the number of hits.
Okay. And do you need 8 hits to do the Kalman filter, or can you do it with less?
For 8 hit what? Sorry.
The question was whether you need 8 hits or you can...
No. I think for the common feature, it's much better. We see a flat efficiency over the eta below at least 3.5.
Mm-hmm.
Yeah. So this is inspired by common cuts, which Atlas and CMS, or close to cuts that Atlas and CMS are looking at for HLHC at mu200.
And they are motivated by what? Because I mean, if we have such a drop in efficiency, that doesn't seem to be very good. So, sorry, I'm asking a very naive question here.
You also you sort of need to correlate this also with the detector geometry. Yeah, if you think about Atlas ITK, in that region at ±2, you start to have around 20 hits, and in CMS phase 2 you also have at this order of 20 hits. So the 8-9 hit flat requirement is actually good enough for this detector, which is the TrackML detector. We have not done such a strong requirement for the forward regions, because we did not want to make a ±4 detector. Yeah.
Okay. Now I get it. Thanks.
No other questions? I see none. Okay, thank you, Xiaokong.
Thank you.
And yes, please stop sharing. And I will resume. Panchali, are you online?
Yes.
Okay, hold on. I will do the sharing myself. Partager l'écran. Yes, your slides should be visible. Okay, please.
So my presentation was about manifold reconstruction using linear approximations. So we see below trajectories of a few particles emanating from an event. And we assume that the track finding has been done. And the reconstruction of these trajectories is challenging due to the low number of hits per particle and the nonlinearity, because it's not even really a helix. So in the figure below, we claim that we can reconstruct these simply using linear methods. And the idea behind this is to select a few points surrounding this given input point cloud, and to consider the map as we show in the next column, which simply depends upon a function of the squared distance between the point cloud and the chosen points. We choose the points such that the image of the point cloud under this map has low curvature. And in this new representation, we apply linear approximation. And of course, this method can find applications in a variety of regression problems, such as the one shown below. For example, we show the denoising of a helix, but the number of points was, I think, 400. And the data was corrupted by uniform noise. So the blue was the input, green is the ground truth, and red is the obtained. And of course, here too, no higher degree polynomial has been assumed. So everything, the approximation has been done linearly. So that was it. Thank you very much.
Thank you. Questions to Panchali? Okay, I have one just clarification. The points, the AI points, they are fixed or they are they change for every event?
So they're with respect to a neighborhood in the data point, and analytically you can compute the curvature. So the curvature lowers, and you select the points such that in the neighborhood it's linear. And I mean, in implementation, what you do is that you choose a collection of points surrounding it, and you put weighting a weight so that it only biases those anchor points, which would enable it to have a lower curvature representation.
I see. I see. Interesting. Quite interesting. Any further questions? Panchali? Okay, so thanks a lot. We have one last talk, which is from, unless I'm wrong, no. Yes, I'm at the bottom of all. Okay, we've gone through all the speakers of last Wednesday session, and so all the speakers are all the session of connecting the dots. We had one last talk from David Langer, who is the main organizer, who has done a huge work and probably not in the condition he was hoping for initially. But okay, we have a whole to adapt. David, I should stop my sharing.
Hi, you hear me okay?
Yes, we do.
Okay, great. Let me just do that. And there. Okay. Very good. Yeah. Hopefully we didn't forget anyone in the QA session. If so, speak up and we can still fix that problem. I sort of put together agendas by hand, and I'm not the most reliable person. So the title page has the beginnings of our workshop photo, which is certainly not the same virtually as it is in person.
David,
but very good.
We're looking at your beautiful screen.
Awesome.
You're sharing your desktop.
It looks fine for me. I don't know what the problem is.
We like the picture or whatever it is, so you can keep talking.
Stop sharing.
That's Kapstadt, isn't it?
It's just a default Mac background, I think. Yeah. Okay, what am I really wanting to share? This. Okay.
That looks
better.
Looks more like.
Okay.
Yeah,
very good. That looks more like a conference photo. Yes. Okay. So very good. Yeah, doesn't measure up to an in-person photo, but we'll try to clean that up a bit. And there's a duplicate problem that we should fix, I think. But that's good. That means lots of people came to more than one session, which is just great. Right. So I just have 2 slides, and not to keep people from getting back to work. So I think we've recorded all the Q&A sessions. We hope we'll get those up on the website soon. I think the recordings have been a success so far, and I think people will continue to make use of them. Certainly trying to view lots of recordings over a weekend is difficult, but having them to view over the next couple of months is less difficult. So for speakers, we will have proceedings process, and we encourage everyone to take advantage of that. Certainly a good way to get something peer reviewed and out there on the archive. We're going to follow essentially the connecting the dots from 2019 procedures, which page limits are on the slide, and more information will come by Monday for templates, deadlines, and how to do things. So watch your inbox. If you don't hear from us, just send us an email and we'll connect that way. We'll also ask everyone who registered to fill a survey if you don't mind. We'll try to keep it to 4 questions or less. But we wanted to get some feedback on how this experimental, at least for us, format worked for this workshop in case we have to do it again sometime soon. Anyway, so speaking of looking ahead, we have a tentative plan that the same that we'll try to do connecting the dots next year at Princeton, of course, world situation allowing. We're targeting the week of May 10 to 14, which if you have a calendar in front of you is the week before CHEP, which Jefferson Lab and Princeton are sort of a plane flight apart, sort of an hour plane flight or maybe 6 hours driving. So it makes sense, especially for those of us living on the Geneva side of the Atlantic. Maybe that saves everyone a trip. It makes for a long trip instead, but it seemed like a practical way to do it. So we hope everyone can come, and this will include the hardware side, the WIT center of the conference, which is the usual odd year system. So please, hopefully everyone can come, and yeah, thanks to everyone who participated. We had more than 200 people register, which is great. If we had that many try to come, we wouldn't know what to do. So hopefully, but that's a good problem to have next year if such a thing happens. And thanks to all the organizers. You got a lot of emails from me, but that's not because I was the only one doing work. The effort of a lot of people, and I gave credit to no one because there's no way I would remember to get everyone to give credit to everyone. And it will certainly be easier to thank people properly in person next year or the next time I see you. So thanks again, everyone. And unless there's questions for me, we are done.
Yeah, and maybe I can say a few words in the name of all of us and in the name of the International Organizing Committee. I share very much what David just said before you started talking, David Rousseau. Thanks very much from all of us for organizing 2 conferences and undoing the organization of 1 conference and being ready to do the conference next year, which I think is just great. And I think the success of the 2 weeks of Connecting the Dots 2020, I think is very much thanks to your all the work you've done. And I think we should give you a virtual clap, everybody.
Very good, thank you.
Actually, we should make an experiment. We all unmute and we clap our hands at the same time. One of those,
I don't know what Zoom does with that.
It might be the end of Zoom. Yeah, I think I'll also want to say that that was really, really nice. I think this conference. I was very, let's say, interested how it would turn out, and I could not have expecting it to work out so nicely. I mean, the talks were great, also for all the speakers, super well prepared. And I think the recordings are actually an asset. Yeah, you can go back and have a look at it. It's a good thing. Hopefully, we learn something additional out of this situation.
Yeah, definitely. And we'll already have on our list to record things next year. But don't let that discourage you from coming. Great. Thank you again, everyone.
Bye.
And we'll see you next year.
Okay, see you next year.
Bye-bye.
Ciao.
Bye-bye, thank you.
Bye.
Bye.
Bye.